In our conversations on double integration so far, we've considered functions in Cartesian coordinates. And we defined our double integral like this by dividing our region up into rectangles and then thinking about the little areas in there as the differential operator. And we found out that we could think about that as a delta x and a delta y, which helped us process this as an iterated integral. And I should have bounds on here, but I don't really know what they are from my picture, so I'm just gonna pretend they're not there for a second. And Fubini's theorem tells me I could reverse the order, but I'm looking at this region, and if I think about increasing in direction of x, well, it's already kind of difficult because I've got like a left function and a right function that changes to a left function and a right function, and changes again to a left function and a right function. Integrating with respect to y would be difficult for the same reasons. And so I've tried to redraw the same area over here, and I'm thinking, well, maybe there's a better way of chopping it up, because it looks like this region starts at an angle alpha and then ends at an angle beta. And maybe I can think of this function as a polar function, r equals f2 of theta. And maybe I can think about this bound, maybe I want that to be a g, g2 of theta. And this one could be an r equals g1 of theta. Maybe there's a way to figure out how to express this double integral using polar coordinates. Well, if I was converting a rectangular equation to polar coordinates, I already know how to make it be a function on r and theta, because I know in polar coordinates x is equal to r cosine theta and y is equal to r sine theta. So no matter what function I was given, whether it's in polar coordinates or rectangular coordinates, I could make it be in polar coordinates. I'm going to go on and add in two more relationships here that might be useful. X equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared, and tangent of theta equals y over x. I could use any of those things to rewrite any kind of equation I was giving in rectangular coordinates down as a polar coordinate function. I just need to figure out what to do with the dA. So let's imagine chopping this up into little polar integrals by thinking about incrementing an angle, delta theta, and incrementing the distance we are away from the pole, delta r. And, well, what would that do? Well, if I imagine starting at alpha and increasing the angle by delta theta, it would just give me another ray. If I think about chopping up the r's as little delta r's, it's like I would get little circles from here, right? There's a little radius, and that's delta r further away. All right, well, if I just do that a whole bunch of times until I've partitioned the whole region, I keep rotating by delta theta. There, I've partitioned the whole region, and each one of those little areas is a little circular sector. They almost look like rectangles in my little diagram because they're so small, but what they really are, if I think about the two arcs, right, they're little circular sectors where the angle of rotation is delta theta, and then this change here is delta r. So I need to talk about the area of each one of these circular sectors if I'm supposed to describe this little change in area here. Right, that's really what I want to describe so that I can get an expression for dA in place of what was dx and dy. Okay, so I need to think about how to find the area of a circular sector, and there's a formula from trigonometry that if I have a circle and I want to find the area of this little circular sector here, the whole thing down, and I'm imagining that this angle span here was alpha, let's say I have a radius of r, the area is 1/2 r squared alpha. And that formula is actually not that hard to derive, thinking about the whole area of the circle being pi r squared. And then the amount we've rotated through is alpha out of a whole of 2 pi. And that's actually how we could establish that formula. So what I realize now is this isn't the whole circular sector, it's a little annular sector, right? I have a big area minus a little area. And that's how I'm gonna proceed from in our fan-shaped region. So I'm gonna get rid of my double integral and rectangular coordinates because it's not what I'm really here to think about. Let's see if we can find the area of that little region. Well, what I really want to think about in the end is a Riemann sum that would look like this. So let's go on and take a point in this region to be r sub k theta sub k. So that little green dot is the polar point rk theta k. And I'm going to use that to help me out. So I know this distance is delta r, and this angle of rotation is delta theta. So what I'm going to do is I'm going to imagine zooming in on that little blue annular sector. So this is the area I'm trying to find. The angle here is delta theta. This distance is delta r, and I've taken a point in the middle to be rk theta k. All right, so what I want to do now is find the area of the whole circular sector, and I'm going to take away the smaller circular sector. So the little delta a sub k I'm trying to find is a big area minus a little area. Right, the area of the whole circular sector minus the area of the little one. Okay, well, using the notation, using the variables I've found, if I think about it, this outer radius, it looks to me to be about half of delta r away from r sub k. So I'm going to imagine that big radius from here to here as being r sub k plus delta r over 2. The little radius would be going the other direction. So the little radius would be r sub k minus delta r all over 2. So I'm ready to put that together with the formula we just wrote down for the area of a circular sector. All right, so the big area, 1/2 its radius squared times delta theta minus 1/2 the little radius squared, and I'm running out of room, times delta theta. Both things have a 1/2 times delta theta. I'm going to factor that out front. And I'm going to go on and multiply these two things out, and some really nice things are getting ready to happen. Again, rk squared. Multiply these together and double it, get rk times delta r plus delta r squared over 4. All right, now I need to do the same thing here. The 1/2 and the delta theta are already out front, but it would be a minus, and I get that rk squared again. So those are going to cancel, and that's really nice. I get minus delta r over 2. Excuse me, minus delta r times r sub k. Those minuses are going to cancel. This is going to double, which is really nice, plus delta r squared all over 4. All right, so altogether, if I look at what that would give me, I have delta theta times 1/2 delta theta times, well, that cancels, these cancel. I have 2 rk delta r's, well, times that 1/2, and this all is equal to, I have 1 rk, delta r, and a delta theta. Delta a sub k is rk delta r delta theta. And now if I think about putting it all together in a Riemann sum, I'd be evaluating my function at that sample point, dA, but we just found out that was rk delta r delta theta, which tells me that the double integral I'm working with is an f of r theta r dr d theta. So the dA becomes an rdr d theta. I'll have to multiply my function by r, and that lets me fill in the blank here. And that will let me evaluate a polar double integral as a iterated integral. I'll just need to remember to bring in a factor of r.